It's a pleasure for me to introduce today's speaker for the Water Talk seminar. Paula Guenther received a Bachelor of Science degree from the University of Wisconsin at Madison in zoology. She began a master's degree program here at the University of Wyoming in the fall of 1986, which she's on the verge of finishing. I understand next week is her thesis defense. For about the past year, she's been working as a fisheries biologist with the U.S. Forest Service on the Laramie district of the Medicine Bow National Forest. Her work there consists primarily of stream restoration and habitat improvement work, although she indicates that she may also do some work related to her thesis research. Her topic today will be minimum pool requirements for trout fisheries in small Wyoming reservoirs. Paula, welcome to Water Talk.
Thanks, Steve. Steve is right. This is sort of a preview for my defense, which is going to happen next Thursday at 9 o'clock in the morning. And for those of you who are going to be here for both of those things, some of this might sound a little bit familiar on Thursday, but if you're listening today and you're wondering why I decided some of the things I decided or came up with some of the conclusions that I did, come next Thursday, because that's when you're going to get most of the data. Today is kind of an overview of the project that I did. I'd like to thank Wayne Hubert for his support throughout the course of this project, and also the Game and Fish, who provided the financial support for the field work and also for my standard of living throughout the 2.5 years that I was working on it. Unfortunately, I haven't been working for the Forest Service quite as long as Steve said. If I had, I'd be looking for a step increase in a little while. But anyway, the minimum pool project that I worked on arose as a result of the need that the Game and Fish had to be able to negotiate for water levels for enhancing or maintaining trout fisheries in small reservoirs. And basically, what happens is there may be reservoirs which currently exist with less than optimal minimum pools, or there may be planned reservoirs that fisheries managers and water developers are negotiating for minimum pools so that trout fisheries can be maintained there. So the goal of this project was to come up with an objective tool for making either minimum pool recommendations or analyzing minimum pools that already existed. And since it was my master's work, I don't have that much input from what the Forest Service thinks about this, but I'm hoping that we're going to be able to use some of these methods on two case studies that we're currently considering, and I'll talk about that more in a couple minutes. Could I have the slides? Okay. I really can't tell whether that's in focus or not. And this is also not working. So if I could, thanks, Tierney. Well, hopefully they'll improve. Okay. The first question that I had to face when I started working on this project is that even though there's a lot of reference to minimum pools in the literature, no one really said what a minimum pool was. They were definitely bad. People were willing to say that. They're not good for fish. But what they were was really kind of unclear. So I considered first the engineering definition of minimum pool, which is a definition which doesn't take any biological considerations into account. It's strictly a structural definition. The minimum pool there is the lowest water level that you can draw the reservoir down to based on what the outlet structure is like. In a situation like the one that's shown here, somewhat humorously, that's obviously not the way to go. So what we did for the course of this project was to adopt a minimum pool definition which took fisheries into account. The minimum pool became the fisheries maintenance pool, and what that meant was that that minimum pool would first minimize the risk of winter kill, which is one problem associated with minimum pools, and then also maximize the standing stock of fish in that reservoir, and in this case we're worried about trout specifically. The reservoirs that we looked at throughout the course of this study were small storage reservoirs for municipal and agricultural water supply. And most of them are high elevation. They're above 6,000 feet. And Because they're above 6,000 feet, they're primarily cold water reservoirs. Some of them may verge on cool water, but they still support a cold water fisheries, primarily trout. In most cases, the trout are stocked. They may or may not be naturally reproducing. We did look at a couple of larger reservoirs with larger impounding structures, but in all cases, none of the reservoirs were hydropower reservoirs. The reason we avoided hydropower reservoirs was because we wanted to model the water level fluctuations that occurred on a seasonal basis as a result of water use, rather than the rapid fluctuations that you get because of pump storage or differences in electrical demand. In all of these cases, the reservoirs have a hydrograph that's dominated by snowmelt. They're low in the spring. When snowmelt occurs, they rise. Drawdown starts right away for usually agricultural purposes. Sometimes when the reservoir is used for municipal use, drawdown is occurring all through the year. So the lowest water levels usually are present by about August or September, and they stay that way throughout the course of the winter. If you have a reservoir that has a steep basin like this one, you can lose a lot of volume and still have the same surface area. But what you get is a very unproductive littoral zone. Often you see terracing like you see here from North Crow Reservoir. Another different kind of reservoir morphology that you can see is a shallow basin like this one. I think this is Granite Reservoir up in Kirk Gowdy State Park. And here, it only takes a really small drop in volume before you lose a lot of surface area. In a reservoir like this, you can see that these shallow areas are going to be the more productive areas of the reservoir. That's where you're going to have a lot of your benthic insects. If you have macrophyte growth for cover or food, it's going to be there. And so when the water's drawn down, you lose those productive areas of the reservoir, and you may be left just with a stream channel that winds through the reservoir basin. Again, the important thing to remember here is that because we get very, very little rainfall during the summer and during the fall, these reservoirs can stay at low water levels like this for the greater part of the year. Okay, when the reservoirs are drawn down, basically two things happen. You get changes in water quality. A lot of times that's just as a result of evaporation or different types of soils being in contact with the water. And the other thing that happens, as I already showed you in those last two slides, is you get a change in basin morphology that can affect the productivity of the reservoir. And there are two components that we looked at throughout this study. The first is the effect of the water quality and basin morphology changes on winter survival of trout. And the second is the effect on standing stock of trout. And when I say standing stock, what I mean is the pounds, or let's be metric, the kilograms of trout that you have per area in the reservoir. So when you hear about biomass for the rest of this lecture, what I'll be talking about is kilograms, and standing stock will be kilograms per hectare. Okay, we'll look at the winter survival component of this min pool model first. Whether or not fish survive over the course of the winter is determined by whether or not there is sufficient oxygen present in the water to sustain them. Trout are a fairly sensitive species. They require about 4 milligrams per liter of oxygen to survive. If there's less than that, for a short period of time they can survive. But if it's prolonged, like the 5 or 6 or 7 month winters that we get in some of the places here in southeastern Wyoming, they can really get into bad shape. So the 4 milligram per liter survival boundary is something that you'll want to be considering as I show you a couple of the slides later that have to do with the oxygen concentrations that we observed. Whether or not fish survive through the winter in a reservoir directly affects the quality of the fishery there, because obviously if they don't survive through the winter, the reservoir will need to be restocked every spring. That's costly, and if you don't get over winter survival, the chances of having a lot of large fish and a quality fishery in that reservoir are substantially reduced. So Obviously, if we could, we'd like to have fish surviving through the winter in all these reservoirs. And I'll give you an idea maybe how we could go about making sure that that can happen in a little bit. In order to figure out just what was influencing the amount of oxygen present in reservoirs, we studied oxygen concentrations for 2 winters on a total of, I believe, 12 reservoirs in southeastern Wyoming. They ranged from plains reservoirs down here near town, Lake Leesenby was one that we looked at, to some very high elevation reservoirs in the Snowy Range. Dipper Lake was one in the previous slide. That was above 3,100 meters, or about 10,500 feet. Obviously, the length of the winter season varies depending on where you are in elevation, and so that was one thing that we looked at. We also looked at a whole suite of physical variables related to reservoir basin shape, and then also climatic variables like snowpack and ice pack, and we also measured water level changes that occurred from site visit to site visit. The goal of all that was to find a way to quantify the variables that influenced winter kill conditions and to find out whether or not they could be predicted or described. The end result of all that was this, which is a winter kill risk rating worksheet. Don't worry about figuring out what all this means just yet, because I'm going to go through each part of it and tell you what it all means. But basically, you go through and you rate winter kill risk based on 5 variables, and you can get a score ranging from 0 to 5. A score of 0 indicates that there's no winter kill risk. It would just have to be an extremely unusual situation for that reservoir to experience low oxygen conditions. A score of 5 indicates chronic winter kill. So you're kind of going to expect to see dead fish floating around the edges of the reservoir every spring there. Three of the variables that we found that were very closely correlated with oxygen concentration was, first of all, reservoir elevation, absolute elevation above sea level, and then the amount of snowpack or ice pack that was present on the reservoir. Obviously, ice pack and snowpack were positively correlated with elevation. But the interesting thing is that there was a real definite negative relationship between snow and ice pack. The more snow you had, the less ice, I guess as a result of insulation. And on reservoirs where there was very little snow or entirely no snow at all because of a lot of wind exposure, the ice got very, very thick. Sometimes you could have both a lot of snow and a lot of ice. This is on Sucker Lakes up behind Medicine Bow Peak, just over 10,000 feet in elevation, and we usually had to dig through 9 or 10 feet of snow to find the ice there. Once we got there, there were only 18 inches of ice, so it was okay. But anyway. So we selected 2 of those kind of climatic variables to describe what I call the basic risk factors. I'm calling them basic risk because there's not anything you can do about them. You could either choose to build a reservoir at high elevation or not, but once it's already there, you're not going to change that. And also, there's not a lot we can do about the weather. So to rate these basic risk factors, what you want to do is consider where the elevation is. And the boundary between high and low elevation is 2,500 meters, or about 8,200 feet, roughly. If you have a low elevation reservoir, it doesn't get any risk points assigned to it. Winter kill is quite unlikely there. High elevation reservoirs are more likely to have winter kill. The same approach with ice cover. If you go out in the field and you take your ice auger and you drill down and you're at Dipper Lake and there's 5.5 feet of ice, I'm kind of skipping back and forth between units here. Anyway, yes, you have more than 50 centimeters of ice, and so you'll have a higher winter kill risk there. The reason behind that is you get a lot of light extinction the more snow and ice you have, and photosynthesis becomes very unlikely at that point. There's no mechanism for introducing oxygen to the reservoir. So use this matrix to assign risk points for the basic risk factors, and then go on to what I call the manageable risk factors. As you're probably thinking, these are the ones that there's a chance of doing something about. One of those was macrophyte abundance. It turned out that the more macrophytes there were present in a reservoir in the late fall, the more likely that there would be low oxygen later in the winter. That's probably as a function of degradation. The macrophytes die, decompose underneath the ice. If there's no mechanism for introducing new oxygen to the reservoir, oxygen is used up and becomes critically low. Macrophytes you may be able to remove. It's not such a big issue in this part of the country, but in the Midwest there are a lot of different strategies for chopping macrophytes out of the lake, or exterminating them chemically, or even introducing herbivorous fish to eat them. I'm not sure how many of those strategies would be successful here. The other manageable risk factor is inflow. If you have inflowing water to the reservoir, it's bringing in a source of oxygen. So if there's any kind of flow through the reservoir at all, you're going to get a little turnover, and oxygen will be replenished throughout the course of the winter. If there is an inflowing stream, winter kill risk is lower. If there isn't, it's higher. Now, before I say anything about this, don't look here and get confused. I was practicing this morning, and I looked and I said, okay, we've got inflow present. That should be low winter kill risk. There should be a 0 there. I said, So these two are reversed, no and yes. So you use the same approach to rating the manageable risk factors here as you did with the basic risk factors. You evaluate whether or not whether or not inflow is present just by going out and looking in the winter. It may take a little bit of digging to find. Or if you have a planned reservoir that hasn't been impounded yet, go out in the fall or the winter and see if you can find inflowing water, going through the stream course. Macrophyte abundance is rated using the Macrophyte Abundance Index, which I developed for use in this project. And it's just a simple visual transect method that you use in the fall. Go out, walk around the reservoir, and rate the presence and abundance of macrophytes, and also of periphyton, or any kind of algae that you see. So between tables 1 and 2, you can come up, I can see, or hopefully you can see, with a range of from 0 to 4 risk points, depending on how bad things are. The 5th risk point comes from table 3 of this risk rating worksheet, and this is what I've called depth compensation. When you look at a reservoir, the more volume that's held in that reservoir when it freezes, the more oxygen there is going to be held in that water. So that means if you have a given level of oxygen depletion that you can expect, a bigger reservoir is going to withstand that better than a small reservoir. At the same time, if you have 2 reservoirs that are, the same size and surface area, but one is deeper, the volume will be greater in the deeper reservoir, and it should have a higher oxygen capacity. So the greater the volume, the lower the risk of winter kill. Where these numbers came from is an integration of the data that I saw in terms of oxygen concentrations and winter kill risk with the depths that were present in the reservoirs that I was looking at. So what this means is if you went through tables 1 and 2 and came up with a score of 0, no winter kill risk, you only need 1.2 meters of water to maintain a trout fishery through the winter. That number is probably a little more arbitrary than most of them, but it's based on the fact that most reservoirs will get anywhere between 25 centimeters and 50 centimeters of ice that develops. And you want to have some volume left over underneath the ice for the fish to move around in. They're going to be a little sedentary in the winter anyway, but they should have some room. That's my theory. If you go through the risk rating steps on table 1 and 2 and you come up with a rating of 3, 4.8 meters are necessary. If you have an existing reservoir that you rate for winter kill, it rates out to somewhere between 0 and 4, and you go out in the winter and you see that there's some depth of water that's less than what's recommended here, chances are you're going to have a problem. It's a little bit easier to see that with an example. So this is an example for Dipper Lake, which, if you haven't guessed it, is my favorite reservoir. It was neat. It's a high elevation reservoir. It's well above 2,500 meters. So it gets 1 risk point for that. It's got a lot of ice, 1.5 meters of ice, as opposed to the 50 centimeter boundary. So it gets another risk point there. It has almost no macrophytes because it fluctuates a lot during the summer, and it's in a sterile, sandy basin. Very, very few weeds. So it doesn't get any risk points for that, but it also doesn't have any inflow. So it gets a risk point there. So the subscore that you get is 3. Go to the table, it says, you want 4.8 meters of water to avoid winter kill. Lo and behold, when I was there, there was usually 3.4 meters mean depth or less, and the oxygen concentrations were really low. So since the reservoir didn't achieve the required mean depth, it gets assigned 1 more risk point for a total winter kill risk rating of 4. That's how that works. Basically what this does is show you how much depth you need to have to avoid winter kill given the basic winter kill risks inherent in a reservoir basin. This is what happens when you take the winter kill risk ratings for the reservoirs that I looked at and you plot them as a function of the average dissolved oxygen observed during the course of the winter there. You can see that low and maybe moderate winter kill risk reservoirs have high oxygen. That's good. It worked. On the other hand, the reservoirs with ratings of 3, 4, or 5 have very low oxygen concentrations, and in fact they're below the 4 milligram per liter boundary that I talked about at the beginning. Those are the reservoirs where you're going to have a problem. What you need to do at that point is look at a way of maybe reducing one of the winter kill risk factors. You can do that by increasing depth, removing macrophytes, or maybe if you have some kind of in-stream flow possibility, arrange to have flow into the reservoir through the winter, if there's any way that you can. If you have a reservoir that's rated 5, like I said, that means it's a chronic winter kill reservoir, and chances are you're just doomed. That's going to be a reservoir where you're going to be stocking fish every spring anyway. But reservoirs with ratings of 3 or 4, I think you probably could manage one way or the other. Okay. This is fun. This is Dipper Lake. This is why I like Dipper Lake. And I thought that when I got my job with the Forest Service and I left the co-op unit, I left my ice auger behind, I left my snowmobile behind. And then I came into work the other morning and my boss, Kent, said, "Paula, I have something for you." And he went behind his desk and he pulled out this beautiful black Forest Service snowmobile suit. So it looks like I'm going to be getting to do a couple more things. One place that we might be looking at mitigating some winter kill risk is on Chimney Park Reservoir. It's a little reservoir near Fox Park. It's on the Boy Scout camp. And it's small, it's shallow, it's got a lot of weeds, and it's got a winter kill problem, most likely. We'll be looking at that. There's a proposal out to dredge it, which is one of those factors you can work on. We can increase the depth. Might be able to avoid winter kill there. So I'm excited. I get to be out in the winter again. Okay, the other component of the min pool model is the standing stock component. Whereas the winter kill component is kind of a pessimistic part of the model. All these fish are going to die unless we do something. This is sort of the optimistic part, because here's where we get the chance to see how much trout production you really could get out of a reservoir. The kinds of effects that you get from drawdown in the summer, I already talked about a little bit. You can lose the upper, most productive parts of the reservoir shoreline, and you can lose those areas that have valuable cover for the fish. The other thing that can happen, and not so much in the really high elevation reservoirs, but in elevations about, oh, I don't know, 7,000 feet, like Shirley Basin Reservoir here, it gets pretty hot out there. And this reservoir gets shallow, and there's very little inflow during the summer, and it really warms up. We were out there, and we were finding water temperatures that were pretty close to the upper limit of trout survival. And we were also finding a bunch of dead trout. So if you could provide, again, for a little inflow or a little bit more depth, you might be able to avoid some of those effects. In terms of figuring out how many trout or what kind of trout biomass you can actually produce in a reservoir, We did 2 summers worth of field work conducting population estimates and water quality testing on 10 different reservoirs, I guess, also in southeastern Wyoming. Again, they were small, and the populations were primarily composed of trout. This is Miller Lake, again, up by Fox Park, Lynn Noel with a real handsome brook trout. Now, the interesting thing here is that this is one of the lakes that I classified as being a winter kill lake, and yet, look at the brook trout. They're going somewhere. They're not there during the winter. I think there's springs in the upper part of the basin where they're escaping to, or they may be going out of either the inflow or the outflow channels during the winter. So the system isn't infallible, but it does give you a pretty good idea what's going on. On the other hand, they stock it every year with rainbow trout. The rainbow trout don't overwinter. We didn't find any rainbow trout that had overwintered. So I guess it depends on the fish. Anyway, the objective of the summer work was to find a way to describe trout populations in these reservoirs as a function of something physical or chemical that was easy to go out and measure and didn't require people to, get their hands wet. What I found was very similar to what a lot of other people have found that did this type of work. First of all, Ryder in 1965, classic paper on the morphoedaphic index, he found that standing stock was a positive function of total dissolved solids, TDS, and inversely related to depth. He used the square root of mean depth. So the higher the alkalinity or salinity, the more nutrients you have in the water, the more fish you get. The deeper it is, on the other hand, the less fish you have. That's kind of interesting since we're dealing with minimum pools here. Gene Whitworth, who was here at UW in 1985, came up with basically the same thing. A, B, and C are just constants. Again, reservoir quality index. Standing stock is a positive function of total dissolved solids and a negative function of depth. In the reservoirs that I looked at, I found, again, a positive relationship to total dissolved solids. Depth didn't turn out to be an important factor. But because it turned out to be a negative factor influencing standing stock in these other 2 studies, that's something to consider. Maybe you don't really want reservoirs to be all that deep if they don't have to be to avoid winter kill. That's kind of the compromise that we're dealing with in this model. The really neat thing I thought about what I found in the summer was this. It really looks like a mess. This is a function of trout standing stock as a function of log of total dissolved solids. And the class 1, 2, and 3 fisheries describe the relative abundance of trout in those fisheries, or in the catches that we found in those reservoirs. Class 1 reservoirs had a catch rate in trap nets that was almost entirely composed of trout. Class 2 was kind of a mixed population. We couldn't really say whether there were more trout or more non-game fish. And Class 3 reservoirs had almost exclusively non-game fish, usually lots and lots of suckers, and not very many trout. What you see here, though, is that for the Class 1 fisheries, there is a really positive relationship with total dissolved solids. That's the one that I showed you on the last screen. But look at what's happening here for Class 2. It goes down. I don't know what's happening there. For Class 3, even as water chemistry becomes more and more favorable for trout production, there's not much of an increase in standing stock. You can see that on the 3rd line there that's almost parallel with the x-axis. What that might be indicating is the result of a lot of competition with non-game fish. That's something that I think we really need to look at further to understand what's going on here, because this was very interesting and not really entirely explainable. At any rate, using the basic production model that I came up with, standing stock is a direct function of TDS plus a constant, you can figure out for a given water chemistry what the standing stock in a reservoir should be. Because standing stock is expressed in kilograms per hectare, if you multiply through by the number of hectares surface area you have, you can come up with the total biomass in the reservoir. The problem is that even though it would be nice to have reservoirs that were always at full pool and always having the maximum biomass. That's not why we're here. Need to be able to identify a water level where the biomass that's present meets management expectations and yet can be achieved even with the constraints that exist on that water storage system. So how to do that was the question. Here's an example from North Crow Reservoir, which is a not very productive fishery up in the Laramie Range. The total dissolved solids is 117 milligrams per liter, which when you consider some of the Plains lakes are up around 14,000, pretty low. It's stocked regularly with catchable trout. And what you see here is a surface area mean depth curve derived from a reservoir planning map at the top. And then for certain incremental water levels, I've extrapolated out to a total biomass value. What that shows you is that at that water level, if that's sustained as the minimum pool, because we've kind of assumed that the minimum pool is what's driving all of this, that's the total biomass you're going to have in the reservoir. You need to, or the fishery manager rather, needs to consider how much fishing pressure he thinks is going to be on that reservoir and how much, harvest he would like to have. He can then mesh that with some estimate of biomass. Let's say he expects there will be between 600 and 800 kilograms taken, because this is basically a put and catch fishery. He might think then that somewhere between 9 and 12 meters or 9 and 15 meters might be a good minimum pool to have. What you also want to do is aim for a minimum pool level where the surface area isn't going to change radically if the reservoir fluctuates a little bit, because they do. So you want to look for places on the graph where the slope is just a little bit flatter, maybe here. Finally, don't forget winter kill. When you're finding a mean depth that you're going to recommend for your minimum pool value, think back to tables 1, 2, and 3. Think back, okay, this reservoir had a winter kill risk rating of 4. It needs 4.8 meters. We're recommending 9. I guess that's okay. That's sort of the compromise procedure again. Maybe, if I'm lucky, I might get out in the field to look for fish during the summer too. One of the real current issues right now is on Sand Lake, which isn't actually on the Laramie District where I work, but it's real next door and it flows down into Laramie District. Wheatland Irrigation District is considering giving up their water rights because it's not worth maintaining the reservoir. In that case, it's possible that either the Forest Service or the Game and Fish might take over management of those water rights, and in that point might be able to negotiate for a minimum pool or recommend a minimum pool. So might get to find out about that. Sand Lake is one of those class 3 fisheries. When we were working there, what we found was we'd pull up a trap net like the ones shown here, and there would be between 400 and 500 little long-nosed suckers about this big. And then there would be about 20 white suckers that were about this big and had nice big heads, and then little arrow bodies. They were really skinny, in really bad shape. And then 1 or 2 teeny tiny little trout. So it's dominated by non-game fish, and it would be nice to turn that around. It's difficult to do that. I'm not saying that just by changing water levels you're going to do that. There might need to be some kind of reclamation, but it's just another thing to consider. Okay, this is kind of a review of where we have been. We've looked at both the winter survival and standing stock components of the min-pool model that I've been talking about here. The model isn't a black box solution. It's not something that you can go out, gather your water chemistry data, measure some things off a map, plug them in, and it'll say, yes, 4.7 meters is the answer. It's just a method to help you evaluate what might be a more acceptable water level. Once you've derived a water level that you think would be good for fisheries, and you're sitting down at the bargaining table with the water developers, the important thing to consider is this just a pipe dream, or can we actually even achieve the water level that I've recommended based on the annual hydrograph of that reservoir or planned reservoir. And that's something really important to consider before you go on and make your final recommendation or give up your last dollar. And this is the thing to consider. What this is a hypothetical annual hydrograph for any one of these small reservoirs I was looking at. The one thing that I've assumed here is that outflow is constant throughout the year. That might be the case in a reservoir that's used for municipal use. If you had a reservoir where the water was used primarily for irrigation, what you're going to find is a little bit of a peak here that follows the growing season. The thing to note here is that at various parts of the year, starting from January 1st and going on, there's either positive storage, which is represented by the area between these two lines, or negative storage. You're losing storage capacity, or rather volume, in the spring and also in the fall and winter. It's really pretty easy to sit down at your computer with Lotus or another spreadsheet and set up a little budgeting spreadsheet that'll show you whether or not, given the inflow regime that you know and the anticipated or known outflow regime and the storage capacity of that reservoir, whether or not you can even achieve that minimum pool recommendation that you're coming up with. It's kind of it's something that you wish you didn't have to do. You wish you could just say, yes, this is the answer, and please use this minimum pool. But I think that budgeting procedure might actually be the key to making this a very, very versatile management tool. With that, I think I'm done, and I'd be happy to answer any questions that anybody has. Dick?
What are the geographic limits or other sorts of limits to the application of your model?
Okay, good question, because I kind of glossed over that. No pun intended. The reservoirs that I looked at basically define the range of conditions that you want to use or apply this to. The reservoirs that I looked at were anywhere from about 5 acres to 100 acres in surface area at full pool. They ranged from, I'm going to use English units here just because I'm thinking that way. They ranged from 7,000 to over 10,000 feet. Again, the 7,000 foot lower limit to elevation is important because we're looking for cold water fisheries here. If you go much lower than that, Muddy Basin Reservoir is actually slightly, I think it's right at 7,000 feet, and it was getting really hot there. The trout were having a really hard time. I didn't define any boundaries in terms of water chemistry, primarily because I had a really large range in the reservoirs that I looked at. Total dissolved solids ranged from almost 0 to about 10,000 in the winter kill reservoirs, and then from about 0 to about 15,000 in the ones that I looked at in the summer. The summer work that I did combined my data with Whitworth, whose equation was up there, and the reservoirs that he used to come up with his models were a little bit bigger. They ranged up to about probably 800 or 900 surface acres. And so that extends the range of the productivity model, but I didn't do anything with winter kill on those reservoirs. So you can't really talk about that, except that in the reservoirs that I saw that were up around 100 acres, there was no winter kill problem. So it would be interesting to look and see. There was also a real strong correlation between elevation and size. The higher you went, the smaller the reservoirs you got. And it would be really neat to continue some of this work looking at high elevation, larger reservoirs like Rob Roy, or I didn't look at Sand Lake in the winter. That would be neat. Lake Owen, maybe. Southeastern Wyoming is sort of the range, though.
Have you tested the model in other areas besides the lakes that you used to develop the model? Or do you have a measure the accuracy of the model for the lakes that you did use?
No. In terms of accuracy, the relationships that I used in deriving this model were the strongest that I had, and they were usually good. They were the model is based on statistically significant relationships, but they're not as quantitative as you might think. In terms of testing, It hasn't been tested. I only had 2 years, 2 winters, 2 summers. But there is money left over from this project, which I'm hoping is going to be used to do some more testing. And in my thesis, there are some recommendations on how they might go about doing that. You might have to read it. Any other questions?
Your example of, what was it, Dipper Lake, where you did the worksheet? Mm-hmm. You said that you came out with a score that indicated it should have a greater depth than you actually saw.
Right.
Did you see anything that supported that would be a problem, such as fish kill in the springtime or something like that?
I wasn't ever up there at the right time to find out whether or not there were, you know, actually dead fish there. The water chemistry suggested that there would be, because it was under ice cover usually for about 7 months, and for about 5 months of that it had oxygen concentrations that were not only lower than 4 milligrams per liter, they were usually lower than 2, and that's really getting low. So no, it would be neat. And one of the things which I had hoped to do but never did get around to doing was going to all of these winter kill reservoirs first thing in the spring and dropping a gill net in and seeing, you know, whether there was anything left over in there. But a lot of times you could tell from the size distribution on reservoirs that I worked on in both the summer and the winter. Like I said, Miller Lake I looked at both. There were no big rainbow trout, and the water chemistry there was basically the same as at Dipper Lake. So I'm basing it on that.
Paul, it looked like when you added your last risk factor point for depth that you could have chosen to incrementally increase or decrease that risk factor based on how much the depth difference exceeded the target.
That's a possibility, but it's not something that I really felt comfortable doing just based on the type of data that I had. But it's a possibility, and that would be something to look into.
Any other questions for Paula? Thank you very much.
Oh. What can I answer for you?
Yeah, I came in late, so maybe I missed it. When you define winter kill, is it 100% winter kill? Is it 75% winter kill, or what?
Well, that's one of the biggest problems here, is that you do get a range of winter kill occurrences. And I guess for simplicity's sake, I assumed 100%, because it was difficult enough to document that, even, let alone different gradations of it. But that would be something else to look at too. Thank you.